Did it ever occur to you that the universe resembles a violin? Correct, it probably didn't, because the universe doesn't resemble a violin, but that doesn't mean it doesn't have strings. Hello, dear friends. In today's video, we'll tell you about string theory, how it originated, what it entails, and how it can influence our understanding of the world. But before we dive into that, we'd like to ask you to subscribe to the channel and hit the notification bell to be the first to see our new fascinating videos about the mysteries of the universe and our planet. The strings of creation are hardly like the ones we imagine. In string theory, they are referred to as incredibly tiny, vibrating threads of energy. These threads are more like tiny rubber bands, capable of bending, stretching, and compressing in all sorts of ways. However, this doesn't mean you can't play the symphony of the universe with them, as according to string theorists, everything that exists is made up of these strings. But let's start from the beginning. In the latter half of the 19th century, physicists believed that there was nothing significant left to discover in their field. Classical physics deemed that there were no serious issues remaining, and the structure of the world seemed perfectly tuned and predictable. As usual, trouble arose from a trivial matter, a small unresolved problem in science, namely, calculating the energy of radiation from an absolutely black body, which means a hypothetical body that completely absorbs radiation falling on it. Calculations showed that the total energy of radiation from any absolutely black body should be infinitely large. To avoid such an obvious absurdity, the German scientist Max Planck proposed in 1900 that visible light, X-rays, and other electromagnetic waves could only be emitted in small packets of energy, which he called quantum. This helped solve the specific problem of the absolutely black body. However, the consequences of the quantum hypothesis turned out to be catastrophic for physics. This became clear in 1926, when another German scientist, Werner Heisenberg, formulated the famous principle of uncertainty. Its essence boils down to the fact that, contrary to all previous assertions, nature limits our ability to predict the future based on physical laws. It turned out that subatomic particles behave entirely differently from anything else in the macroscopic world around us. At the subatomic level, the fabric of space becomes uneven and chaotic. The world of tiny particles is so tumultuous and incomprehensible that it defies common sense. Space and time in it are so warped and intertwined that there are no ordinary concepts of left and right, up and down, or even before and after. There is no way to determine with certainty in which point of space a particular particle is at any given moment. There is only a probability of finding that particle in some region of space-time. In Einstein's general theory of relativity, as in a state with opposing laws, things are fundamentally different. Space is depicted as a trampoline, a smooth fabric that objects with mass can bend and stretch. They create deformations in spacetime, which we perceive as gravity. As a result, the correct and understandable general theory of relativity finds itself in an insoluble conflict with the tumultuous quantum mechanics, making it impossible for the macro world to reconcile its laws with the micro world. This is where the time for string theory comes in. Many scientists are confident that everything in our world can be explained by one fundamental physical principle. But how did this theory come about? Even to this day, not all physicists are enthusiastic about string theory, and at its inception, it seemed infinitely distant from reality. It all began in the late 1960s when a young Italian theoretical physicist, Gabriele Veneziano, was searching for equations that could explain the strong nuclear interactions which bind together the nuclei of atoms, uniting protons and neutrons. In the end, after years of work, Veneziano noticed that the Euler function, which had long been considered a mathematical oddity, described this strong interaction very well. This helped the scientist find the formula he was looking for. In the end, it caught the eye of a young American theoretical physicist, Leonard Susskind, who saw that primarily the formula described particles that had no internal structure and could vibrate. Susskind realized the formula described a string similar to an elastic band. It could not only stretch and compress, but also oscillate and twist. Thus, the revolutionary idea of strings emerged, which most scientists greeted rather coolly. At that time, the accepted science represented particles as points, not strings. For many years, physicists studied the behavior of subatomic particles, colliding them at high speeds and studying the consequences of these collisions. It turned out that the universe was much richer than could have been imagined. It was a real boom of elementary particles. Physics graduate students ran through the corridors shouting that they had discovered a new particle. There weren't even enough letters to designate them. However, the question of why there were so many of them and where they came from remained unanswered. This pushed physicists to an unusual and stunning prediction. They realized that the forces acting in nature could also be explained with the help of particles. That is, there are particles of matter and there are particles carriers of interaction. For example, a photon, the particle of light. The more photons, the brighter the light. Scientists predicted that it is precisely this exchange of carrier particles that constitutes nothing other than force. Scientists believe that if we were to go back to the moment just after the Big Bang, when the universe was trillions of degrees hotter, the carrier particles of electromagnetism and weak interaction would become indistinguishable and unite into single force called electroweak. And if we were to go back even further in time, the electroweak interaction would merge with the strong interaction into one overall superforce. Quantum mechanics suddenly explained how 3 out of 4 forces interact at the subatomic level. Moreover, it explained it beautifully and consistently. This elegant picture of interactions ultimately received the name Standard Model. But even in this perfect theory, there was one major problem. It didn't include the most well-known force at the macro level, gravity. For the theory of strings, which hadn't yet blossomed, it was like autumn as it contained too many problems from the very beginning. For example, the calculations of the theory predicted the existence of particles that, as it was soon established, didn't exist. For instance, the tachyon, a particle that moves faster than light in a vacuum. Among other things, it turned out that the theory required a whole 10 dimensions. By 1973, only a few young physicists were still grappling with the mysterious calculations of string theory. One of them was the American theoretical physicist John Schwarz. For 4 years, Schwarz tried to tame the unruly equations, but to no avail. Among other problems, one of these equations stubbornly described a mysterious particle that had no mass and was not observed in nature. The scientist was about to abandon his futile endeavor when it dawned on him perhaps the equations of string theory describe gravity. Assuming that the strings are billions of times smaller than an atom, the theory's flaw turned into its merit. The mysterious particle now acted as a graviton, a particle that had long been sought after and which would allow gravity to be transferred to the quantum level. This is how string theory complemented the puzzle of gravity absent in the Standard Model. However, even this discovery did not elicit any reaction from the scientific community. String theory remained on the brink of survival. Only one scientist wanted to join his quest, ready to risk his career for the mysterious strings, Michael Green. In the early 1980s, Schwarz and Green tried to resolve the unsolvable contradictions within the theory, and they succeeded. But what astonishment it was for the two physicists when the reaction of the scientific community towards string theory began to change drastically. Literally within a year, the number of string theorists skyrocketed to hundreds. It was being called the theory of everything, as it seemed capable of describing all the constituents of the universe. As everyone knows, every atom consists of even smaller particles, electrons, which orbit around a nucleus composed of protons and neutrons. Protons and neutrons, in turn, consist of even smaller particles, quarks. Quarks consist of tiny, vibrating threads of energy, resembling strings. They are so small that if an atom were enlarged to the size of the solar system, the string would be the size of a tree. Different combinations and vibrations of these strings give particles their unique properties, such as mass and charge. Since ancient Greece, physicists have been accustomed to the idea that everything in this world consists of something like spheres, tiny particles. And now, having barely gotten used to it, they are proposed to abandon this paradigm altogether and operate with some kind of spaghetti scrap. Although many scientists call string theory a triumph of mathematics, it still has some problems, primarily the lack of any possibility to experimentally verify it in the near future. No instrument in the world, neither existing nor potentially emerging, is capable of seeing string. But, to be honest, seeing strings is not necessary at all. To prove string theory, something else is needed, something that sounds like scientific fiction. Confirmation of the existence of additional dimensions of space. What is this about? We are all accustomed to 3 dimensions of space and 1 of time, but string theory predicts the existence of other additional dimensions. But where are they located? The answer to this question was given by the Swedish physicist Oskar Klein, who suggested that the 5th dimension is curled up billions of times stronger than the size of an atom, so we cannot see it. The idea of the existence of this tiny dimension, which is everywhere around us, lies at the heart of string theory. But in reality, the equations of string theory require not just 1, but 6 additional dimensions. They all have very twisted and convoluted shapes, and all of them are unimaginably small. In the mid-1980s, string theory acquired a majestic and elegant appearance, but inside this monument there was confusion. In just a few years, a total of 5 versions of string theory emerged, and although each of them is based on strings and additional dimensions in detail, these versions diverged significantly. The paradox is that all 5 versions can be considered equally valid today, but which one truly describes our universe? This is another puzzle of string theory. But the main problem, as already mentioned, is the inability to prove their existence experimentally. However, some scientists believe that the next generation of accelerators offers a very minimal but still a possibility to test the hypothesis of additional dimensions, although most are confident that if it is possible at all, it will happen not very soon, at least decades, and at most even hundreds of years. Thank you very much for watching. If you enjoyed this video, don't forget to like it and subscribe to the channel to not miss our new interesting videos about the mysteries of the cosmos. Write in the comments what you would like to learn about in the next video. Thank you and see you next time.